Okay, so the electric potential. So for the electric potential, we need to know that work done from A to B, point A to point B, in moving the charge is equal to change in potential. This is point A, this is point B, and we move the charge in the field from this point to that. And work done from A to B is equal to change in potential. This is a proposition. So VB minus VA is equal to so once again we do this thing. VB work done from A to B is equal to VB minus VA, and also work done is equal to from A to B is equal to delta U, the change in intensity. So VB minus VA is equal to change in intensity by okay, wait, there's a small point missing. Basically, very delta V is equal to basically delta U by Q naught. Okay, this we know. So what we have is VB minus VA is equal to delta U by Q naught. We start from here, we use this, and we get to this one. Okay, so once again, slight simplification, delta V is equal to delta U by Q naught, and delta U becomes equal to Q naught delta V. Okay, the reference point charge into the potential difference gives us the intensity change. This is tricky, but worth the time. And at a point, the potential at a point, VB minus VA is equal to work done from A to B by Q naught. This is understandable from the work above. So basically point A has null charge, no potential. VB minus 0 is equal to work done by Q naught. Work done from A to B in this case becomes from infinity to B. Work from infinity to B. Okay, so we get VB, the potential at that point is equal to work by Q naught. So this becomes another form, and this time we call it V, not VB. Okay, because at A there is no charge and no potential because it's infinity. Electric potential now is gradient. Electric potential is gradient. Potential gradient basically, as we know from theory, is equal to change in potential by change in distance, delta V by delta R. This is worth noticing. And work done from A to B is equal to F delta R, force into distance. Okay, and basically F delta R cos theta. F we know is equal to minus EQ naught. Okay, and the electric field into the reference charge with negative sign gives us the force, and so in this case what we are working with is F delta R cos theta is equal to minus EQ naught. We equate these two. No, sorry, excuse me. EQ delta R, work done from A to B. This and force, okay. Force and distance. No. It's a mistake here. We don't equate. We estimate the work done from A to B in terms of the electric field, which is minus EQ naught force and the distance delta R, and then the cos theta, where theta is 0 degrees, which makes it 1. So work from A to B is equal to minus EQ naught delta R. Yes, and work done from A to B divided by Q naught is equal to minus E delta R. and work by charge is potential difference, as we have established. So delta V is equal to, or work from A to B by Q naught is equal to delta V. So now we take this as 1 and take this as 2, A and B. Yes. So and now we have an easy situation where we can easily equate, and it gives us minus E delta R is equal to delta V. Yes. And E in this situation will become delta V by delta R with a minus sign. And this is the gradient. Potential difference by differential distance is the electric field as a gradient. So this is what we establish in this kind of situation. Electrical concepts are tricky business, so one has to be very vigilant with the quantities and notations, basically every fundamental. Now we have capacitance. We are moving slowly today, actually tonight, because we're trying to avoid mistakes. So we have capacitance. So capacitance is with this situation where we have storage of charge, and the charge in this case is directly proportional to voltage, and with the constant of proportionality this becomes CV, and C becomes Q by V. The constant of proportionality becomes charge by voltage. Okay, beginning with the proportion, Q is proportional to V, Q is equal to CV, and C is equal to Q by V, and C is the constant of proportionality, which is capacitance. Okay, we have a parallel plate situation, and we have a schematic for it as well. The plus charge in this sheet, the minus charge in this sheet, and here is the circuit with the battery plus and the minus charge, and here we have this voltage 1 and voltage 2, and here we have this distance d. Okay, from the gradient we know that E is equal to minus delta V by delta R. Delta V is equal to V2 minus V1, and delta R is equal to D in this case. So E becomes minus V2 minus V1 by D, and E is basically V1 minus V2 by D, and V1 minus V2 can be approximated to V. The difference in the voltages of point 1 and 2 is roughly equal to V for simple notation. So this electric field is equal to V by D. So this is an equation, the voltage by distance, because we have one battery, so basically one source of potential difference, so we can use the sign V here. And density, we know that sigma is equal to Q by A. Okay, sigma is equal to Q by A. Charge by area is the density, and we will carefully use these forms, which are basic ones, so everything will not be derived, but some basic forms will just be used. So E is equal to sigma by epsilon naught. This is also known, so we know this when we will use this as a substitution, and maybe this one as well, we'll see. E is equal to sigma by epsilon naught, and sigma is equal to Q by A. So basically we will reverse the order. E is equal to sigma by epsilon naught, density by permittivity is the field, and sigma is equal to Q by A. So E is Q by A epsilon naught. Yes. Okay. You see, so this is the situation. So now we have two forms for E. One is E is equal to V by D, and the second one is E is equal to Q by A epsilon naught. So V by D is equal to Q by A epsilon naught. What this gives us is Q by V, very smartly, Q by V, this is what we're looking for, gives us A epsilon naught by D, and Q by V is equal to C, the capacitance. Okay, this we know from here. Let's call it a substitutional notation A. So now we know that capacitance C is equal to A epsilon naught by D. So this becomes the equation of interest. And C vacuum, because C vax, the capacitance for vacuum is equal to A epsilon naught. Epsilon naught is the permittivity in the vacuum by D. So this is noticeable. We also have a dielectric situation. If we have a little dielectric, so the C of medium, the capacitance of medium would be A epsilon by D, and epsilon would be epsilon relative epsilon naught. So C with medium, capacitance in a medium, contrary to the vacuum, would be A epsilon R epsilon naught by D. Yes. which means C medium is equal to epsilon r into C vacuum. Yes. Let's call it 3 here, and let's call it yeah, 3 is enough. After that we just have the substitutions for permittivity. And now we can discuss the capacitors. In series, in parallel, and then there's resistance, charge to mass ratio. We'll see. Okay, so we will do some basic stuff only, and we'll leave the rest to next session. So we discussed the capacitors. And we have this little form, the schematic, which says plus plus minus minus, and the battery here plus minus, and then capacitor 1, capacitor 2, plus plus and minus minus, and then